Okay, thank you very much. I must admit I was not involved in setting up the program today, so I was also surprised to find out that I'm the first speaker, but I'm deeply honored to offer it. And so I'm very much looking forward, and I'm also looking forward to the full program. And I fully agree with everything that Jörg has been saying, but you see, I'm a surface scientist by training, and I was exposed to electrochemistry like 20 years ago. What I want to show you a little bit is my struggle with electrochemistry. And I think of course, the fluctuations are important, but there are also more fundamental concepts about how you describe electrochemical interfaces that they are also important. And I dare to say that I have the feeling that there's still lots of misconceptions around. And of course, you always have to be careful. When I started electrochemistry, there were always the old guys who said in electrochemistry everything has been already solved. The problem was it has been published in a Russian journal in the 1960s and has never translated to English. So that's why the world is still waiting for it. But there's still a lot of confusion. The strange thing is now I also belong to the old guys and the other ones died out. So let's see. So that's sometimes the advantage. But I want to, in the beginning, I want to, and so first of all, I will talk about challenges and concepts in the modeling of electrochemical interfaces, and then also provide some example of our work. So I'm here the representative of the atomistic world, and I'm looking forward to learn a lot of things of the guy from the continuum world. Okay, so just it's a general interest. Why? I mean, the strange thing is electrochemistry almost was dead 20 years ago. Nobody was interested, but now, due to the importance of electrochemical energy and storage, this is, of course, a major research field, which is very important. And this title is not my title. I've stolen it from a director of the Fritz Haber Institute, Robert Schlögl, and I like this very much, from free electrons to bound electrons, because this summarizes what electrochemical energy storage and conversion is about. We have this volatile energy sources. We want to store the energy. And what is the best way? It's the chemical bond. I mean, you can ask, of course, also if you have this water pumps or so, they are also efficient, but they need much more space. So if you think of density, the chemical bond is the most efficient one. And so that's why you have to say the current you want to store it in a chemical bond. And this is the same in a battery and also in fuels. And often people kind of do not see that this is true also in batteries. And so now the general topic I've been working on the last 20 years, interfacial chemistry, and it's concerned with structures and processes at the interface between an electron and an ion conductor. So it's very simple. And the examples are fuel cells, batteries, electrocatalysis, electrolysis, photocatalytic water splitting. There's also now, there comes a picture that I stole from you. So there are also processes that one would rather avoid, these corrosion processes. Or I think I searched for my own picture. You have another one, so to say. And then even in life science, you have membranes and these processes. So and we in principle work here at this topics here in my group, and also in last time a lot of battery research, but also electrochemical interfaces. Okay. Now, but the problem, you see, I'm a surface scientist by training. And it was a great time, or it's still a great time, to work together with experimental colleagues. They have an ultra-high vacuum, they have a surface, they deposit CO on it, and you have a perfect structure, and it's a perfect battlefield or a playing ground work for theoreticians and experimentalists working together, because they have the same atomistic information. Now here, when you come to electrochemistry, you have this electrolyte. An electrolyte, of course, you can have solid electrolyte, it's liquid. A liquid is a liquid is a liquid, which means with our tools, in DFT calculation or when you do Gaussian, you have this button, optimize. So you start with the structure, push the button, optimize, and it finds the next minimum. This doesn't work here anymore. We have to do the averages. And so how can we deal with this complexity of electrochemical, electrolyte, electrode interfaces? And that's, again, statistical averages. As you mentioned, we have to do statistical averages. And also, I now also have this included picture, the Nobel Prize for Chemistry for the lithium-ion battery. This was, in fact, also telling that the research of lithium-ion battery is not only a technological endeavor, it's science. It's basic science, and these three gentlemen were involved in it. There's a story from my perspective of Ulm. Stanley Whittingham was in the city of Ulm giving a talk when Stockholm called him. But he was giving his talk, and so then they called this conference organizer, and so she was standing there as a good colleague of mine with a cell phone at her hand and had Stockholm at the phone and had to wait 20 minutes before Stanley Whittingham could finish his talk, and then he was only learned that he got the Nobel Prize. So this was an interesting event. Okay. So again, so this development from lithium, I won't talk too much about batteries, but it's not only technological advances, it's also, it demands successful basic research. This is, so to say, my theory slide, my method slide. So we do periodic DFT calculation, standard periodic DFT calculation. I don't want to talk about it. And again, the challenges. So what are the challenges in the theoretical treatment of electrochemical solid-liquid interfaces? Again, liquid electrolytes require to perform statistical averages. Free. So that means also in principle free energies instead of total energies have to be determined. Then there is one parameter, and I said I'm a surface scientist. A parameter that is new when you come from surface science is the electrode potential. And I also want to spend some minutes on the definition of electrode potential. And also, again, the electrolyte, an electrolyte also, of course, you have to have solvated ions there. So it's also, and then it's automatically also a reservoir for ions. So whenever you do calculations, you have to look what is the concentration of, let's say, sodium or chloride, and they can absorb. So you have to take this into account. So you also have to work a lot of with thermodynamics and chemical potentials. And in principle, it's simple. We just have to do reliable quantum chemistry calculation of these interfaces, and they should be performed under potential control, whatever this means, with an appropriate number of electrolyte molecules considered and their statistical nature taken into account through averaging over sufficiently long ab initio molecular dynamics simulations, so to say. So brute force calculation, but they are not doable, and they won't be doable. I mean, I will show some examples where we think we can approach this step by step, but there won't be doable, so to say, in a general sense, and that's why we have to deal with, and we have to find methods how we deal with this complexity in a realistic fashion. And this is also what I guess is the workshop about, and I'm looking forward to it. Okay, electric double layer. There's a good colleague of mine, and he had this in this once Elsevier reference model, he wrote electrical double layer forms whenever two conducting phases meet at an interface. And now I have to admit I'm a physicist by training. I've now been for 20 years in the chemistry department, but as a physicist, you always like to ask after the driving force. And this is, I mean, okay, I exaggerate things just to make the point. The chemists just say it's there. And then they give arguments, yeah, there's rearrangement of molecules, but why do the molecules rearrange? What's the driving force for the building up of the electrical double layer? And you don't find it. And here it's also the models. You see, that's also how we discuss electrical double layer. We use the first is the Helmholtz medal from the 19th century. You have this dipole layer, this Helmholtz layer. Then Gu and Chapman introduced this diffuse layer, and Stern combined them. And you see, there must be a lot of truth in those, because they are still cited and cited and cited again. You read reviews says, we know that electric double layer consists out of its staying layer and the diffuse layer. But this is a 100 years old concept. So I think we have the tools now to check whether this is really the case. So I'm not questioning this concept, but it's still strange that it's, so to say, taken for granted. We already know the structure. And again, also, often no explanation is provided why the electric double layer forms. I want to give you an explanation that has been motivated by work of Mira and Jörg, because they kind of made me alerted me about the fact that in principle electrochemical interfaces are relatively close to, for example, p-n junctions, or let's say a Schottky contact. The p conductor would be the ions, the n conductor the electrons. And so these are examples, and also then they published some very nice work about how semiconductor defect chemistry can be connected with electrochemistry. So then, the only thing I changed here is that I rounded it up, because in liquids you wouldn't have the spike here. That's the only change I dare to make to this work, so to say. And also the difference, of course, is if you do defect chemistry, the defects are rather stable and not mobile, while in a liquid electrolyte, of course, you have very mobile ions that can move and rearrange. And now look at Wikipedia, and there's this in the p-n junction. You see and in the p-n junction, what you also have is in principle electrical double layer. They do not necessarily tell this, they tell it space charge region, but the space charge region is nothing else but electric double layer. I also forget to make one point. This is about electron neutrality. And sorry, I have to go back to this because this is an important point. It's also the question, do we deal with charge systems in electrochemistry? And you see, when I first presented this, I made a very embarrassing error. I had here 6 minuses, or 6 pluses and 5 minuses. Why do I appreciate this, to emphasize this? The electric layer always has to be neutral. Why is that? If it was not neutral, it's conducted to 2 conducting phases. There would be a net field, and the field would then rearrange it. And also electrochemistry, I'm now only talking about equilibrium conditions, so where you have a chemical potential. Everything is neutral. I mean, the electric double layer, of course, those 2 parts are not neutral, but the overall is neutral, the electrode is neutral, and the electrolyte neutral. They're all this charge balance. So this is also important because one hears a lot of things about what's the charge. I mean, there are charges moving, this is true. But overall, thermodynamically, the material is charge neutral. So in fact now in semiconductor physics you have then the space charge region. Again, they have to compensate this layer. But why is this there? And the semiconductor physicists know it, to align the Fermi energy. That's the reason. Or you could also put it in a more general way, to align the chemical potential of the charge carriers. Because at the end, and again, what I'm talking mostly about is thermodynamic equilibrium. So we are always talking about equilibrium conditions. And so the driving force, again, is the Fermi energy has to be constant throughout the whole system. And why is this argument hardly used in effective electrochemistry? I mean, you see, I expose myself because electrochemists do not work like the word Fermi energy. So, because they're not material scientists. But then I would say that you could call it the electrochemical potential of the electrons. I have another point when I say the electrochemical potential. You know, the electrochemists make a distinction between the chemical potential and the electrochemical potential. And then they say, okay, what do we do? There's a difference. It's electrostatic forces. But if we look at our Hamiltonian, if I look at the Hamiltonian that we use in quantum chemistry, what's the ingredients? Kinetic energy, electrostatics. Everything is electrostatics. Every covalent bond is due to electrostatics. So I also find this distinction between a chemical potential and electrochemical potential artificial. How will you do the separation? So this is all the question that okay. Now, electrochemistry and potentials. And the electrochemistry is characterized by a multitude of potential definitions, some expressed in units of voltage. And then also, of course, we have the chemical potential that are expressed in energies. And I was also very confused. And I was so happy when I saw this paper in 2021, ACS Energy Lenter, Potentially Confusing Potential Electrochemistry, where they also say there are so many chemists. And you see, you find papers where they say the potential. The potential is that. And this is what they say. The word potential alone should be avoided unless the type of potential is made clear. And it's often not clear. Is it the electrostatic potential? Do you describe, you saw my electric double layer, we have electrostatic potential. Or is it the chemical potential, which should be fed? This is often not specified. So this then also contributes to the confusion in this system. And also one thing, we was exposed to, I was then exposed to battery projects, and we had one project, insertion of sodium ion in the cathode at high potentials. And you see the driving force, I will come to this in a minute, in a battery is that the ions move from the anode to the cathode. So that's the driving force. But for the electrochemist, they move up the potential. And I'm a physicist. You always move down. I mean, it's like downhill. I mean, you roll down a hill, you don't roll up the hill. But you also have then, because of the charge convention, you sometimes have to go up the potential, which I also found very confusing. So I was first wondering what my colleagues wanted to tell me about that. Okay, and now, how do you picture the role of the electropotential for yourself? And you see, when I started in Ulm, there was the late Professor Kolb, who was also a background in surface science. He was a long time also at the Fritz Haber Institute. And he told me at that time, the electrode potential plays a similar role in cyclic voltammograms as the temperature and temperature programmed desorption. So I don't know whether you're familiar with temperature programmed desorption in surface science. You deposit some molecules on the surface, and then you ramp the temperature in a linear fashion and just measure what's coming out. You can't cycle it because it won't go back, so to say. So the advantage in electrochemistry is, you can cycle it. And apparently, the change of the electropotential is something like a change of the temperature. And then I also looked up, this is interesting, electropotential and electromotoric force in Hindi. And, but I like this very much because the electropotential here, it says its tendency to lose or gain an electron is called electropotential. And you see in principle, this is like a chemical potential. It's measured in Wolf, and also important, it's an intensive property. It's independent of the amount of species, and also it means in principle that it has to be constant in thermodynamic equilibrium, if you consider this as a thermodynamic quantity. And then you see, I like Wikipedia very much. But when it comes to electrochemistry, I think it's all electrochemists have written this, and they are so much concerned about measuring. And so when you write, here, I copied this also as Wikipedia to last year, I don't know whether they changed. In electrochemistry, electrode potential is the voltage of a galvanic cell built from a standard reference electrode and another electrode we characterize. Again, I mean, I would simply say, and I dare to say this now, and you can beat me later, it's nonsense. Okay, yeah. That's right. No, you see now, that's what I said. I'm now in Germany. Since I have now been longer in the field, no experimental electrochemist that I know is safe of me. I approach them and I involve them in discussions all the time, and I will also tell another discussion that I have, so to say. And then by convention, the reference electrode is the standard hydrogen electrode. It's defined to have a potential of 0 volt. But again, I mean, of course they are true. You have the 3 electrode, and you measure it. You have to have a reference electrode in order to measure it. But again, as I just said, in principle, if you have an electrochemical cell in equilibrium, the cell itself, there's no voltage. There's a voltage between the reference electrode and your working electrode, but not between in the cell itself. And then origin interpretation, again, also Wikipedia. Electrode potential appears at the interface between an electrode and electrolyte due to the transfer of charged species across the interface, specific adsorption of ions at the interface, and specific adsorption rotation of polar molecules, including those of the solvent. Again, here they I think, mix reason and consequence with this. They say this, and you know, now I'm whenever I find an experimental electrochemist in Germany standing for 5 seconds, I approach him and says, can there be an electropotential without an electrode? And maybe I will then come to this point later, and they say no. But I will now say so exactly this, can there be, and now so from again, I continue. In electrochemistry, the standard hydrogen electrode, abbreviated SHE, is a redox electrode which forms the basis of the thermodynamic scale of oxidation reduction potential. The hydrogen electrode is based on the redox half cell corresponding to the reduction of 2 hydrated protons into gaseous hydrogen molecule. Is there an electrode? You define the reference electrode, there's no electrode. It's a cycle molecule. So even there is no electrode. And so now, and then now I now have here this how you can define electrochemical potentials. And for example, we know, and this is then Jens Nørskov has written up and now called computation hydrogen electrode, that we can define the at finite pH in a hydrogen. So this is how the 0 of the standard hydrogen electrode is defined. And we know also how it's changed if we change the electropotential and the pH value exactly in this fashion. So this is now, and in principle at the left-hand side, you have these chemical potentials. And now there, of course, I'm not daring to say that I'm the first one to start with this discussion. This has been already been performed for decades, and especially Trasati has written some very interesting papers, and some colleagues says they don't like him. And this is here already in 1986, Trasati wrote, the electropotential is often misinterpreted as the electrical potential difference between a point in the bulk of the solid conductor and a point in the bulk of the electrolyte solution. So it's already there, written 40 years ago. And the thermodynamic reference state is a solvated electron in the liquid phase. I consider this to be wrong. Because a solvated electron is a very short-lived species. I know this from Fritz Haber Institute. Martin Wolf has measured them. You can, with lasers excited, and then it lives for 3 femtoseconds. the reference state is, in my opinion, of course, the chemical. It's the electron. It's the chemical potential of the electron, and not the solvated electron, because this is not a species that lives very long anywhere, so to say. And again, then the energy of electrons in a vacuum just outside the phase is in fact adopted by physicists to measure the electronic energy in the bulk. This reference state is suitable to rate the potential scale of electrochemists with the energy scale of physicists. To make a long story short, that means we have to measure the work function. And again now, so in thermodynamic equilibrium, again, I only talk about thermodynamic equilibrium, electrochemical potentials, concentrations, and hence also the electropotential, they have to be uniform in the whole considered system. I'm not talking about the cyclic voltammogram, because there you change something, but if you then have equilibrium condition, everything has to be constant. This is the very definition of thermodynamic equilibrium. And the electrode potential is an intensive thermodynamic property, like the temperature, that in equilibrium has to be uniform throughout the whole electrical system. That means, again, both an electrolyte and electrode. I mean, we have an inhomogeneous system. We have an inhomogeneous system, but we assume thermodynamic equilibrium, so the chemical potentials have to be constant, period. And that's why, in my opinion, the electropotential is nothing else but the Fermi energy, or if you wish, the electrochemical potential of the electrons. And then it's also, sorry about that. Now I come back to this point, is there an electrode potential without an electrode? And I have very, very prominent electrochemists says no. To be honest, in principle, as I said, they are concerned with electrons. It's like, assume you have a plastic container. Plastic because there's no interaction, and you have an electrolyte, a soup inside. This is to say, it doesn't have a temperature. I mean, we assume it's if there's no thermometer. This doesn't make sense. Of course, you can't measure it, but it doesn't. If you assume a system is in equilibrium, it has to have certain values for the thermodynamical parameter, even if you can't measure it. So this is the interesting thing about this field. Now, I change gears a little bit, and I'm now talking about operating mode in batteries, because we also do a lot of research. We have this cluster of excellence, post-lithium storage, and this is taken from a review article by Islam, and this is how a battery works. And in fact, it's very easy for us DFT guys to calculate open circuit voltage, and this is given here, taking out this. So in principle, what is the basic reaction? What is, again, as a physicist, I ask myself, what is the driving force? What is the driving force that if we close the outer circuit, we can here get work there? And in principle, you see this definition. What is the reaction upon discharge? I will talk about the word charge. And you see, in principle, you have lithium in the anode, and you have lithium already in the cathode, and afterwards, there's more lithium in the cathode. The driving force is simply that the lithium atoms are more strongly bound in the cathode than the anode. And then what you can calculate here is the free energy. So the energy gained upon the lithium transfer, this is an energy. But you know, if you do thermodynamics, in thermodynamics, you know that if you start from the first point and the second point, the way doesn't matter. It's independent. Now, how does the battery work? These strange Germans not, the strange battery people, they put here an electrolyte. An electrolyte is an ion conductor per definition, and an electron insulator. So, of course, it always has some electrical dynamics, but let's, for the sake of the argument, say it's an electron conductor. So, and then the electrons can't go there, and then they have to take a detour. But the basic process is that once you close here this outer circuit, then the electron can happily go there and meet their friends, the lithium plus cations, and rejoin, and then are happily after forever then once they're there. And this is the driving force. And that's how we also then calculate the open circuit voltage. We take the free energy divided by the Faraday constant. If we make this, calculate this in V, F would be 1. And then it's just 1 for a monovalent cation and 2 for bivalent. And that's how we can calculate. And you see, it's the difference of the chemical potential of the lithium in the anode and the cathode. And I'm doing that so slowly because I have the feeling that not a lot of people are aware of this. And also, the thing is, again here, note, a battery is never charged. I'm a proud owner of a battery electric vehicle. I now make also commercial. It's an ID.4, of course, it's a German car. We love it. And I also, of course, say I go to a charging station. But you never charge a battery. There is no charge. And I mean, of course, sometimes you find the right impression in literature. You lithiate or delithiate anode and cathode. This would be the proper name. But again, I mean, everybody. And also the strange thing is, how do the battery people measure the performance of their electrodes? By a capacity. Now, as a physicist, for me, a capacity is charge over voltage. But for a battery guy, capacity is just charge. And then they have specific capacity, charge per volume and charge per weight. This is what you read. And so, but there is no charge. It's atom, it's concentration. I understand that it's now, once you have a nomenclature, you stick to it. But again, you use a nomenclature that is kind of misleading to a certain extent. And sorry that I emphasize this so much and that I make such a strength point. And 2 years ago, I would be a little bit more modest about this, but now, since my retirement is close to come and nobody wouldn't harm my career anymore, then I can make this point, so to say. And now, one interesting point is still, the point is, why do you measure? I mean, you see, I say here, this is free energy. Why do you measure this at the outside? It's strange. I say it's a chemical process, and it has nothing to do only with the electrons, but why is this there that we measure it? And this is also very interesting, and I wrote it up, and I think this is one of the things that are published every 10 years in new papers, then people forget about it, and then some other rediscovers it, so to say. So again, so we think about a battery, we have the chemical potentials in the anode and cathode, and we can then subdivide this chemical potential into, now I word electrochemical potential of the lithium cation and the electron. And now we do a Gedanken experiment. We just have this two anode and cathode, but connected by vacuum. Now, what are the properties? Of course, they are not in equilibrium. Our reference state can only be the vacuum. And I particularly made this that this is my zero, and these two add up to this point. And then, again, the chemical potential in the anode is lower, and it's larger, and this difference is the energy gain. Now, I introduce an electrolyte. What happens if I induce electrolyte? Again, per definition, an electrolyte is an ion conductor and an electron insulator. So it means that I connect these two with an ion conductor, and if I wait long enough, I have to have thermodynamic equilibrium of ions. So this is then here in the next picture. So what happens if I introduce this? I have here now my electrolyte, and now these two chemical potentials of the lithium cations have to be aligned. How are they aligned? They are aligned through the building up of electrical double layers at both anode and cathode. There's an electric field acting on it which pushes these two levels together. But now we have the electrons. And now you see also interesting thing. Mathematically, you know the electrostatic force is 1 over r. So if you go from here to there, no matter what you go, you always feel the difference in the electrostatic potential. So the electrons feel exactly the same field, but they have the opposite sign. So by the same amount of energy that the levels of the cations are pushed together, the electron levels are pushed apart from each other. And that's why at the very end you measure here the total voltage. So it's electric double layer. And you see, I know also that there are more and more studies about electric double layers. They are important. The only problem in battery research, also for theoreticians, is that the electrode and electrolyte interfaces are much more ill-defined than in, for example, in electrocatalysis. And that's why it's much harder to do this. But I think there is one should also put effort in looking at the electrical double layers that there are in the batteries. So, and then at the very end, you just measure here the voltage. There's another point that I came across also, and so the open circuit voltage is entirely given by the difference of the Fermi energies in anode and cathode under this open circuit conditions. Now, when you read literature, battery papers, you often find lithium is the best electrode or best anode because it has the lowest redox potential. Also, I mean, this is strange. Why is it strange? Because redox potential, what is the redox potential? It's the energy difference, or you put an electron, so lithium plus lithium. But that's not the whole story. You know, it's about chemistry. And so then you find here this lithium, but what I just told you, in principle, what matters is the cohesive energy. It's not, and this is a part of it, admittedly. But so to say, the cation part is missing. And so in principle, what you should look at rather is the cohesive energy or the binding energy in the metal that corresponds to the cohesive energy. And so then when you look it up here, then you find lithium has still a very relatively small cohesive energy, for example, compared to gold and silver, which have 5 eV, but sodium and potassium, they are of smaller energies. So in principle, you could say that there would sodium and potassium. Of course, you have to combine it with the cathode where it's bind strongly. But also this argument, again, is, in my opinion, nonsense, so to say. And okay, I also want, the point I want to also make is that and I don't have the foils here. Then the question also asking, how much can we improve batteries? You know, there was some time 10 years ago this 555 project in the US. Everything should be increased by a factor of 5. Now, what you see here is the cohesive energy. What's the best anode? It's the metal anode. And I was at a battery conference, and the question was, why is there no Moore's law for batteries? You know, the batteries were introduced commercially by Sony in 1990, and they have been increased their capacitance by a factor of 4 linearly over the last 30 years. So why is there no Moore's law? I mean, the semiconductor people know Moore's law because when you first stored a bit or so, you had huge areas of material, and then you exponentially decrease the size. But what's the charge carrier here? It's already the atom. We can't make it smaller. And also, the metal anode, there is no better metal and no better anode than the metals. Because if you would have a material that, of course, you want to have a low binding, but if you have an anode that binds lithium, for example, less strongly than the cohesive energy, then it would never get in. Then you have this plating. We have already the best. So when we hear things of saying, yeah, we increase the capacity of battery of 10 times, it's nonsense. There are physical laws prohibiting it. Of course, there's still room, and a lot of room, but it's different from semiconductor physics. There is no room at the bottom anymore. We are already there at the atomic level, so to say. Okay, another thing about now, you see, once I'm in the mood, I also now will criticize a Nobel Prize laureate, but I don't want, it's not only me. So also interesting thing is, why do we still have flammable electrolytes? You know, the concern about that some, now one does, I can remember 5-10 years ago, whenever there was a Tesla burning, there was a news report all over the world. Now, apparently people get used to this, and it doesn't happen so often. But why are the people in battery research so stupid and use flammable electrolytes? You have to take into account that the voltage of a lithium-ion battery is about 4.5 EV volts. And you see, I'm a physicist by training, but I learned that, of course, that means upon, now I also use the word, let's say lithiation, delithiation, used once under strong oxidizing condition and strong reducing conditions. So you have a material, you expose it. And you also need electrolyte that has a large electrostability window. And there are only few. Maybe it's so to say, we have all this ethylene carbonate and so on going on. There have been lots of tries with water and salt concepts and also ionic liquids, but we still use these flammable ones, so to say. These are the alternative concepts and so on. And now I have also, I always use this for summer schools when a Nobel laureate is wrong. There was a Jacques paper by Goodenough in 2015, and he says, so to say, he used this potential interference, and he then wrote, the electrolytes are supposed to be stable if the electronic band gap is larger than the open circuit voltage. Again, what I also found strange, I felt uneasy with that, because here you have a purely electronic thing, and as I just told you, this is a chemical thing. So that doesn't really fit together. But there came somebody to my rescue, and there's a paper, and I recommend this paper in 2018 in Energy and Environmental Science, the electric potential window of battery electrolytes, the HOMO-LUMO misconception. And I will also already make the point, the most prominent electrolyte whatsoever doesn't fit into this picture, which is water. Water has a HOMO-LUMO gap, if you define it, you know it's a liquid, 9 EV. And it has the electrochemical stability window of 1.23 volts. So this is, again, this counterexample. So also, in principle, if you just have thought about water, that you would have guessed that it's nonsense. And in principle, what matters are the redox potentials. It's not the HOMO-LUMO gap, it's the redox potentials. But you see, once when good enough writes a paper like this, then you find this and cite it all over, and all people just repeat this. And when I say a summer school, sorry about this, then I tell to the young students, I also often didn't understand things in my life, and to 95% it was my own inability to understand things. But there are 5% of things where communities sometimes have found perspective, and they never question them anymore. So also the younger here, I asked you, don't trust anybody above 30 who's giving talks. No. Again, my personal experience is mostly, of course, scientists are not stupid, but sometimes they are also human beings and they are just following the crowd. So okay. Now, okay, this was my introduction. Now let me give my introduction into some structures. So as I said, I'm a DFT guy. So what we did was then really molecular dynamics simulation. We looked at metal surfaces, here platinum. We had 6 water layers in a 6x6 surface unit cell, and we ran it for 40 picoseconds and looked at the distribution of the water film. And this is a snapshot and so on. And then also the questions, how did we change the electropotential? And this is, in fact, you see we have here a vacuum cell, so we can measure the unit cell, the work function, and we use the concept of Trasati. And also, the expert of you know that this discussion about the 4.44 EV or so, but this is exactly what we use. And how do we change the potential? We changed it by adding or taking away hydrogen atoms. So once we have here 144 water molecules, and if we have one OH molecule, then the electron is immediately taken from the Fermi energy of the electrode, and we have, so saying this changes the Fermi energy. Or if we have an H3O molecule, it becomes automatically H3O plus and transfers its electron to the Fermi energy. And also here you see also how the simulations. This is now the work function over the runtime, and we had 2 simulations in red with the 6x6 unit cell, and here in blue with the 3x3 cell. And you see these fluctuations are more or less a matter of the size of the system. If we were able to do a 1,000 by 1,000 cell, it would be more or less flat. It's like then also the same when for example, grand canonical and microcanonical all become the same. So this we have here the same. And now here you see what we do, and the problem of course is we change the pH strongly, but if we in our cell add 1 hydrogen atom, we change the electrode potential by 0.1 volts and then have different conditions there. So, okay. Here, this is also one example to just what we did there was just trace single oxygen atoms of the water molecules. This is only to tell you how dynamic the system is. So we just marked 1 oxygen. Of course, we can number them. And then you see here, even there are some strongly adsorbed, and you see all of them more or less. We only had here 2 which stayed there. All other molecules were constantly changing position back and forth, even those ones that are a little bit more strongly bound on the surface. So it's a very dynamic system. And now here, I must say, this is hidden in this foil. I'm proud of DFT. Why I'm proud of DFT? So we now did also, I told my postdoc, do a calculation of the most boring system. Why is that? Because silver is known to hardly bind anything on the surface. So even if you have electrolyte, it's so inert. That means, why did I want it? Because we wanted to make sure that we have a clear water layer there, and this is consistent with with the experiment. Now, if the potential of zero charge of silver 101 is minus 0.3 volts. So it's a regime where water is not stable in principle. I was always surprised that the electrochemists do experiments from minus 0.5 to 1.8 volts outside the electrochemical stability window. But apparently the systems are so inert that they still survive. But so Sung did also the work, and he added 2 hydrogen atoms there. What happened? They recombined. It never happened in platinum. Platinum has the work function and standard hydrogen electrode of 0.5 volts, so where water is still stable. So DFT made it correctly. They realized, I know I'm checking, but the calculation realized we are in the conditions where water is not stable, and when we have high, and that H2 formation is stable, and when we have 2 hydrogen ions there, they form H2. This never ever happened in our simulation with platinum also when we had, so to say. So this gave me some trust in that this is correct. And here there are some details. I don't want to talk about this so much. Also, we had some now just a cooperation with also former co-worker of Larry, Mats Melander, about free energies. So in principle, what we do is in principle still molecular dynamics simulation, and you could then set up an thermodynamic cycle. I don't want to talk about the details, but it culminates here that one then calculates solvation energy, and you see you have here the absorption energy, and here you have the free energy, and you see that here's the binding energy. It's the so to say the binding energy from the molecular dynamics simulation, and the free energies are reduced a little bit more than by this strongly binding water molecule, because here there's less entropy when it's bind, so to say. So one can also go to free energies if one wants with this method. A very short detour to implicit solvent. We started with implicit solvent. We did calculation for methanol oxidation. You can compare methanol oxidation in gas phase and in electrochemistry. And interestingly, they have two different routes. In electrochemistry, it goes over formate and in methyl oxide, and in gas phase, you form this molecule, and we could also reproduce this with this potential, because the one, you see the difference is that the one species has OH group, the other one not, and then the implicit solvent does it correct. You stabilize the species with the OH group, so everything's fine. But here then I took this from a paper of Carr and Chan's group, and here they compared the absorption energies in implicit and explicit water, and they got differences up to 0.6 eV. So there's still the question, how reliable are the implicit solvents? So I was hoping when I was exposed to it, and now Richard is not here, but he introduced this Wasssol, and our first calculation was with Wasssol, but I came also a little bit disillusionized there through these results. Then also one final point. Yeah, I've still 6 minutes. You see, this is a picture from 2013. And I showed this picture at that time to the late Professor Kolb. And he said, what you're doing has nothing to do with electrochemistry. I do not fully agree with that yet, but what he meant is the following. So when you typically have a platinum-water interface at the potential of charge, what you have is this here. So platinum is always hydrogen covered. Of course, the experts know that there is the window where there is a region where it's a free surface. But of course, again, and I'm just making this point, whenever you do electrochemical interfaces, you have to take into account what's the surface coverage of the ions. Now, of course, you could say, let's run a molecular dynamics simulation. They would take much too long. And I will show you that's easy for certain systems to find the coverages. And the idea is here, Carsten is still not here. Carsten wrote up this ab initio thermodynamics, which in principle is a grand canonical scheme. They didn't invent it. It's just combining atomistic description with the chemical reservoir, so to say. So, but it has been very successful in surface science. You just define your gas phase as a reservoir. You don't have to explicitly treat it. And then you just ask yourself, and if you change, for example, the partial pressure and the temperature, then you change the chemical potential, and you can then derive temperature and pressure dependent potential energy surfaces and also phase diagrams. Very nice. Now, and in principle, the computational hydrogen electrode that was introduced by Jens Nørskov is exactly the same. But the only thing is that he said, okay, the problem in electrochemistry is that we don't have a molecule as a reference state, we have a solvated ion. And most people know that solvation energies, so they're a pain in the neck to calculate. And then the idea was of Jens Nørskov just saying, but we have another reference. We just look at the standard hydrogen electrode. We know that at standard condition, for example, the proton is in equilibrium with the hydrogen molecule. And then why not use this as a reference? This is all about what there is computation hydrogen electrode. You see, Jens Nørskov doesn't need to be defended by me. But I hear, or maybe I misunderstand, I hear so many papers, or see many papers beyond computation hydrogen electrode. This means beyond thermodynamics, in principle. I know what they mean. There's a lot of approximation. I will show you some approximation, and you have to find out whether they work or not. But what these people who say beyond computation hydrogen electrode, in my opinion, was they mix is the concept itself and the approximations that are mainly used when applying this concept. And okay, so now you have again the formula, so we can now express this here, and in principle, then we can use this, and this doesn't only work for hydrogen, we can do it for every species where we know a redox potential. So for example, I will show some halides examples, and then we just look up Wikipedia, there I trust Wikipedia, and then we get this number, and then we can get it, can also get here free energies of absorption. And then the question is, how realistic do we have to model the system? Do we have to take into account the full electrolyte? And I will show you some examples. Okay, here, halide adsorption. Halides adsorb like hell on surfaces. They have even at very low concentration, they have a very strong overlay, and it's a closed layer. And the fact is, so what in principle, and to make a long story short, I will show you we do not need to include the water or the aqueous electrolyte there, because they bind so strongly. At the same time, they are very small. They build a very flat layer, and so we did just surface science calculation. We did surface science calculation, and you see, for example, here we had square root 3 times square root 3 layer, and then the water is just flowing above it, and it's weakly interacting. So the presence of water hardly matters here. Then here, we calculate this absorption energy as a function of coverage, and all what I show you in the coming is based on this number, nothing more. Then you use here two-dimensional diagrams. You have the chemical potential, for example, of chlorine and hydrogen electrode, and then you can get such a phase diagram. It's here the stability, or it's a phase diagram of hydrogen and chlorine co-adsorption on platinum 111. And there's one embarrassing thing that I might not tell you. We tried to publish this paper here, and we presented this, and then the referee said, "Why don't you calculate Pobe diagrams?" And we said, yeah, it's a good idea. We hadn't done it before. Later, the colleague asked me myself and said, oh, you should have known that I was this. This was Mikkel Spriek. But I usually do not play the game to try to find out who the name is, so to say. But Mikkel Spriek told us to use, you can also now, again, this is, again, no electrochemist would plot anything as a function of the electrochemical potential of chlorine and hydrogen. And for example, if you run a cyclic voltammogram, you would go along this line. And then you could here also look more detail. And here there's a lot of interesting things that I don't have time to talk about. But then you can also just make a transformation into a Pobe diagram. And then you have a Pobe diagram. And what I want to tell you here is they are almost semi-quantitatively correct with respect to the experiments. I have another example to show this. This is the adsorption of bromine and hydrogen. And this was a paper from Filio in 2018. And they are nice to plot the cyclic voltammogram as a function both of standard hydrogen electrode and reversible hydrogen electrode. And for example, you see here, you have here one peak here. This is constant at standard hydrogen electrode condition, means it's not pH dependent, so there's no pH, there's no hydrogen involved. This is the chlorine or the bromine layer. The other one is moving here. So both under, this is the hydrogen peak, and it's moving both under reversible hydrogen electrode and standard hydrogen electrode. And then the electrochemists would say non-Nernstian behavior, whatever this means. In my opinion, it's still non-Nernstian. And why is that? And I go back here for the expert. You see, the non-Nernstian behavior is if we jetzt move this here, the electropotential, we move here with pH, we also change it here. But now we have to look, we have here competitive adsorption. At a certain point, hydrogen is replaced by the highlight, and then we have to look where do this point cross, and since there is a slope, it's not flat, we have a different value, so it's no longer the 59 millivolts per decade, and that's why we get, you can derive that this is this formula that gives you this this experiment. And okay, now I have a last example, even with it more complicated, I will just use 1 minute. Sulfate. Now, sulfate is not, you see, the advantage of these halides is they're so strongly bound and so small, it doesn't matter whether there was water. Sulfate is a different beast. It's looking upwards and so on. And first of all, it didn't work when we just used also implicit solvent didn't. One of the things is that if you know from experiments that in this row you have strongly adsorbed water. So this is water, this is bound by 0.8, 0.9 eV. This is in principle ice-like water. So you have to take this into account first of all, and also implicit solvent. And then again you get these phase diagrams, and then you get here also Pobe diagrams, and they are also almost so again here we had to take into account some explicit water and also implicit water. And you see here there's even a curved line. And this is because Fernanda is a very clever electrochemist. She also took into account that you have an equilibrium between sulfate and bisulfate. And if you do this, you get also this curved line. And this is almost on the spot with experiments. And there was also another paper. Okay, now I'm 3 minutes over time. So of course, I have a very short conclusion. I just want to thank all the people and agency that helped. So of course, we needed funding, we needed computer time, but most of all, we needed people. This is my group who contributed to this work. So I thank those guys for their contributions for their work, and I thank you for your attention.